So great, good morning, and I guess we are ready for start with Chris' last lecture.
Thank you, and thank you all for being here. I know it's Friday and it's early, so it's not trivial. So last time, you'll remember that we finished proving this theorem, which told us that in these fixed QES subspaces, exactly what the QES means in terms of reconstruction. It told us that CFT subregions can reconstruct operators in their entanglement wedge. And then we asked the question, well, maybe these operators, are better than the guarantee this theorem is giving us. Maybe they just always work. Maybe this like CFT operator O always reconstructs phi. It just works. That's just phi in the boundary. But then we saw, no, that's not the case. That subregion reconstruction implies this very strong thing that the operators you use on the boundary to reconstruct bulk operators really only work in a subspace. You really shouldn't expect them to work more generally. We should just say that O works in this fixed QES subspace, not necessarily more generally. Remember, so it works, so OB works as phi in some code subspace. Or if we're calling code subspace like the bulk, the image of the code subspace under V. But in this Hilbert space, this subspace, not more generally. Kind of unfortunate because, maybe there's more to life than just fixed QES subspaces. And in fact, that is the case. We will see that if we want to talk about black holes and reconstructing operators in black holes, we're going to have to talk about things besides just fixed QES subspaces. So let's prove that to ourselves. Let's say we have a very natural question. We have, this is ADS-CFT time slice, and then in it there's some black hole. This is the horizon of the black hole on this time slice. And we want to reconstruct some operator inside, because we want to know what's going on inside the black hole. And we want to map that question to the boundary and answer it there. So we're going to continue talking about whether we can reconstruct this phi on some subregion of the boundary, say this subregion B. It will also be an interesting question. Can you reconstruct this if you allow yourself to use the entire boundary? It's weird, I can hear myself in the other room. But talking about the subregion reconstruction question is completely general because you can always take the subregion to be the entire boundary at the end. So if we understand subregion reconstruction, that's a stronger understanding than asking about whether we can reconstruct it if B were the entire boundary. And you'll see we'll learn some important lessons by continuing to focus on the subregion reconstruction question. Good, okay, so we want to reconstruct phi. Can a subregion do it? A subregion like B here. Okay, so theorem 1 guaranteed that we could, if we restricted our attention to a fixed QES subspace, and in this fixed QES subspace, all the quantum extremal surface was, say, like this. So the black hole was included in B. We couldn't reconstruct it on B if the QES was, say, something like this, excluding the black hole. So the question is, if we have a black hole in general and some large enough boundary region, can we reconstruct is the black hole in the entanglement wedge? Okay. So the problem is black holes have sufficiently large Hilbert spaces that they're not going to nicely fit in a fixed QES subspace unless the boundary region is very, very big. Here's the precise statement. Let's say the black hole is in some natural black hole state. Maybe it's a thermal state. But let's say it has horizon area A. That's its horizon area. We know if it's in a thermal state, technically that has support on, okay, if we took an honest thermal state of the black hole, that would be a state with support on the entire Hilbert space of the bulk, right? Like an honest thermal state at some temperature has support on every state. That's very big, so it's certainly not a small subspace of the bulk. It's certainly not going to be a fixed QES subspace. But we can say, well, many of those states have very small support, right? The thermal state is decaying exponentially with energy. So perhaps we don't need to take all of the states in the Hilbert space when we talk about a black hole at some temperature. We can just take the important ones with a significant amount of support. Okay, as Brian mentioned, I think in his second lecture, you can do that, so you can like sort of chop off the tails of the wave function, and then this black hole will have support only in a subspace of dimension, and I'll write it here. So right here. So if you want to say describe some natural black hole, like a thermal state black hole, the Hilbert space that the state will have support in will have a dimension that's like e to the a over 4g, at least. Let's say that that's, yeah. Strictly speaking, when I say e to the a over 4g is the dimension of the black hole Hilbert space, what I'm talking about is the number of states you need on the boundary, like the CFT Hilbert space, to that the dual thermal state on the boundary has support in a Hilbert space of this dimension. And for now, we can just imagine this describes the state of the black hole in the bulk as well, that it's some object with a Hilbert space of this dimension.
Chris?
Yeah.
I thought that would be true even if we didn't cut off the tails of the support on Hilbert space of the black hole. What's the answer in that case?
Technically, the thermal state, like a black hole at some temperature, will have support on every state.
I guess, so are you saying that without this cutting off, the black hole entropy is greater than A over 4G?
No, the entropy is A over 4G.
Okay.
But the rank of rho thermal is very large, even though S of rho thermal is like A over 4G. It's not maximally mixed. If it were maximally mixed, then the rank, or the log of the rank equals the entropy. But if it's not maximally mixed, say if it's thermal, then they can be very different.
Amazing, thanks.
Yeah. Okay. So all of this discussion is to say, we're imagining the black hole is basically this object in the bulk with a Hilbert space. It's some quantum object with a Hilbert space that's this big, which is pretty big. And we know that if we took, say, the thermal state restricted to this, every state has roughly equal support, but we can even consider the most entropic possible state in this subspace here, the set of states we restricted to. We could call that rho maximally mixed, which is basically the identity in this black hole Hilbert space here, normalized by the dimension. So this, we could just consider this state. This is one of the black hole states that lives in this subspace, and it has a very large entropy. I mean, it has this entropy. It's a calculation that you can do. Okay, so now the thing to note is, let's take a definite setup. Let's consider that we're working in a 2+1 dimensional bulk. Although this will work in any dimension, but I can tell you precise statements in that dimension. So let's take B to be some fraction of the boundary, let's say more than half. There are two, if you look at the geometry, there are two competing extremal surfaces that could be quantum extremal surfaces depending on the state. One is this one. So there is a classically extremal surface that goes here. Let's say B is like 60% of the boundary. There is a classically extremal surface here. We'll call it gamma 1. And there's another one that excludes the black hole. We'll call it gamma 2. And so the question, these are the two classically extremal surfaces. And so whether or not, with our attention focused on this subspace of the bulk, whether or not the black hole is in the entanglement wedge of B depends on which of these two surfaces is the quantum extremal surface, or which is the minimal quantum extremal surface, right? That's the prescription for finding the entanglement wedge. And the point is going to be that that's going to depend on the state. That, let's say, so if we take this black hole to be pure, so it's in some state, I don't know, like E, or some state psi, some pure state. You just pick one of the pure states in this Hilbert space where the bulk is in a pure state, and in particular the black hole itself, which is we're treating as some quantum object, is in some pure state. It has 0 entropy, and in this geometry, it turns out that gamma 2 has a much larger area than gamma 1. So I'll write it this way. So area of gamma 2 is quite a bit larger than the area of gamma 1. Okay. So if the black hole is pure, then gamma 1 is going to be the minimal QES because, right, so the decision of which one is the minimal QES is just a question of, is the area of gamma 1 plus the entropy of the black hole less than area of gamma 2? Plus any entropy that's in here, but in this subspace we're considering, we're just neglecting the possibility that we're putting entropy there. Okay. And if the black hole is pure, then the S of black hole is 0. And by our assumption down there in the setup, this was the case. Area of gamma 1 was less than area of gamma 2. So the black hole is part of the entanglement wedge of boundary region B. So let me say something. So this depended on B being more than half the boundary. So if B were less than half of this circle, this inequality would go the other way, which kind of makes sense from symmetry. But that's just something you can compute if you wrote down the metric for, say, BTZ and looked at it. Okay, so I've argued to you that we have this Hilbert space, this subspace of the bulk we're considering, and in one of those states in that Hilbert space, the black hole is in the entanglement wedge. And now I'm just going to argue that in a different state, say that the black hole is not in the entanglement wedge. Gamma 2 will be minimal. And the reason is that, again, we just have to ask which way does this inequality go? And so now, S of black hole in let's just pick one of the states. I know that the maximally mixed state is going to be the most entropic state in this subspace. So I'm just going to consider that one, just because I can. So the entropy of the black hole state, and say the maximally mixed state, I claim, for now, we'll put a question mark here, and then I'll argue it to you. So this is equal to A over 4G. And so indeed, this left-hand side, the area of gamma 1 plus the area of the black hole over 4G. Sorry, I'm not putting 4Gs here. I should be putting 4Gs here, because the whole question is whether or not, which is the minimal QES, right? So that's a question of minimizing area over 4G plus entropy. So here, all of these should be over 4G. Okay, so indeed, when the black hole is maximally mixed, it's not obvious, right? Because we had our assumption that gamma 2 is bigger than gamma 1, but now perhaps the area of the black hole is big enough to make the inequality go the way written here. And indeed, that is very often the case. So like, let's say, for example, the black hole is of order the ADS radius. So let's just say, like, for definiteness, we're considering 2 + 1 dimensional bulk, black hole now of ADS size. You know, that's medium sized. That's like the smallest sort of big black hole you could have. And okay, if this is the case, so you write down the BTZ metric, you assume the black hole is this big, and then you can find the extremal surfaces for B of different sizes. And what you'll find is that in order for, so this inequality is true unless capital B is at least 7/8 of the boundary. Okay, so if the black hole's ADS size, B needs to be about or greater than 7/8 of the boundary to have the black hole be in the entanglement wedge. If it's smaller than 7/8, let's say it's like 3/4 or something, then we get the interesting physics. That's what I want to talk about. So I want to specialize for now to the case where B is a little bit smaller than that, but still greater than half. This might seem very specific, but you'll see the point in a second. Okay, so like I literally mean B is like 3/4 of this circle here. So because it's not quite as big as 7/8, then when the black hole is in its maximally mixed state, it's not in the entanglement wedge of B. So maximally mixed black hole, not in the entanglement wedge of B. But because B is greater than half, the pure black hole is in the entanglement wedge of B. Okay. So all of this was to say that there is just it's very easy to find situations where you have some black hole and maybe you want to reconstruct an operator in that black hole, but you can't do it on the subregion you're considering, at least according to Theorem 1, because the black hole doesn't fit into a fixed QES subspace. Like the black hole's, like, let's say it's in the thermal state or something, the subspace you have to consider to even describe that black hole is so big that some states in that subspace put the black hole in the entanglement wedge, and some states do not. Okay, so it's not a fixed QES subspace. The QES depends on the state in the subspace. All right. Okay. So this is me arguing that it's very easy when you're considering black holes to run into this situation where you're not living in a fixed QES subspace.
Sorry, just one question. What if your black hole is like in a superposition of a maximally mixed state and it like
and a pure state?
Yeah.
Okay, yeah, that's a great question. So if you just consider the state where it was like a like half this plus half this.
Yeah, exactly.
Yeah, so then the entanglement wedge actually wouldn't even be well defined. So this is something that Jeff and I studied. This is what Jeff mentioned in his second lecture at the end.
Oh, that's true.
Yeah, then the entanglement wedge would sort of be in this weird superposition of being, including going up to gamma 1 and going up to gamma 2. And we should just say it's not well defined there. It's not like some sharp one of those.
Okay, yeah. And so, okay.
Yeah. Okay, great. So this poses a problem because Theorem 1 only guaranteed a sort of reconstruction that worked in fixed QES subspaces, But we sort of started out on this whole program of bulk reconstruction because we wanted to talk about reconstructing operators on black holes. But black holes don't generally fit into these fixed QES subspaces. So what we'd like is some generalization of Theorem 1, maybe a Theorem 2, that tells us what the QES formula tells us about reconstruction more generally, without the assumption of living in a fixed QES subspace. All right, and that's what we have, so I'm going to write that now. So it's going to be Theorem 2. So the goal is to understand reconstruction when your code subspace is larger than just being a small fixed QES subspace. And this theorem comes from a paper by Jeff and me from last year. And I'm going to write the theorem down. I won't prove it to you because the proof is actually just very similar to the proof we gave for Theorem 1. In fact, that's why we went through the proof of Theorem 1. Just a few minor tweaks. And the proof exists in this paper. I will give you intuition for what it says, though. That's my goal. So the assumptions of Theorem 2 are very similar. We're just dropping the fixed QES assumption. So again, we have some H physical, which we're assuming factorizes into B and B bar. So of course, you should consider something like a B and a B bar here. And we divided the boundary into 2. And then also we have H code, which you should imagine is divided into H little b and H little b bar like before, which again is going to be morally like little b is the entanglement wedge of capital B and little b bar is the entanglement wedge of capital B bar. But now, instead of this being like a fixed QES subspace, it's like a arbitrary subspace of the bulk Hilbert space. And this is still like HCFT. This tilde just means morally like. Okay, and now before I go on, there's some additional structure that we're going to allow at this point. So let me motivate it. So in this is all the structure we needed in the Hilbert spaces to state Theorem 1, because the QES never changed depending on the state, right? So the little b was always the entanglement wedge, little b bar was always the entanglement wedge of capital B bar. We didn't need any other structure. Now we're going to see that the entanglement wedge will depend on the state, won't always be little b. And so to handle that, we're going to have to consider how the bulk is divided up into little pieces. So I'm going to put down extra points. I'm going to say we're going to allow the bulk to have some spatial factorization. So, in little b, there will be like a little b1, a little b2, a little b3, and so on. Little b4, all the way to like little bn. And there will also be, we're also going to allow little b bar to have a little b bar 1, little b bar 2, all the way to little b bar m, let's say. Okay. So these two Hilbert spaces, we're allowing them to factorize like h little b1 tensor all the way to h little bn. And then likewise, this guy can factorize h little b bar 1 tensor all the way to h little b bar m. Sorry, that's really small. That's a little m.
So, Chris,
Yeah.
so your definition of B and B bar is for any state there will maybe different QS, and you're saying, yeah. So it's just B and B bar are like for that state, for that QS, you'll have this entanglement with.
Yeah, you're saying, yeah, why am I calling some preferred set little b? Yeah.
Yeah, I just wanted to make sure that, yeah, so you can have different QS,
Yeah.
and B will be always be though the entanglement wedge of B, big B.
Oh, good. Yeah.
Right?
So like we can consider a different state where like the entanglement wedge of capital B is like this, perhaps.
Right.
Which like so it excludes this guy, but it includes this one. And
And you wouldn't call so the second region that you draw now, would you call it B, a little bit or?
good. So yes and no, but mostly
Okay.
yes.
Okay.
So as we'll see in the statement of the theorem, we're gonna assume a state, psi, and then we're gonna just, and little b will be morally the entanglement wedge for that one state. And then other states would be different applications of the theorem, and then like, when talking about those other states, yeah, you would call this little b. Yeah.
Okay.
Okay, so far we've just written down some structure that's gonna show up in the theorem. So these is before finite dimensional Hilbert spaces. And these little guys you might think of as just some spatial factorization of the subregions. And again, there's going to be this V, which maps you from H code to H phys, H physical. And then finally, as Gulo just alluded to, we're going to put in the assumptions of the theorem that there's a particular psi we're going to talk about. You'll see why. So this is different from Theorem 1. In Theorem 1, this was the setup of the theorem, and then the statement was 2 statements are equivalent, and each of those statements said for all states. Here, though, because different states have different entanglement wedges, the right way to do it is to just talk about one state at a time, because we're going to talk about one entanglement wedge at a time. Okay, so psi goes here, and we're going to assume psi is some state on B bar R. So R here is going to be some extra reference system, possibly entangled with little b and little b bar. And we're doing this so that we can talk about general states on little b bar, but we want to write a pure state in the statements of the theorem, so we're just going to purify it by adding an arbitrary reference. So in the picture, you should imagine that all these guys are just entangled. There's some extra reference hanging out. R, just separate. Okay. So this is some state in H code, tensor H capital R. Okay. Now, so the Theorem 2, like Theorem 1, is going to be a statement that 2 conditions are equivalent, one being the QES and then one being a reconstruction statement. The reconstruction statement is going to be slightly different, slightly weaker, because we have weaker assumptions. We're not assuming we're in such a small Hilbert space. But before I can write the equivalence, I need to define one thing for you. So under this, I'm going to define something. I'm going to define product unitaries. So whenever I say product unitary from now on, I'm referring to this. Yeah.
You might have said this, I might have missed it, but you're assuming that the Hilbert space in the bulk factorizes? is that an exact statement, or in this specific case, or in general have?
Yeah,
what
good.
there is a
So
context?
in the statement of this theorem that I'm writing down, yeah, we're assuming they exactly factorize. To apply this to ADS-CFT, you could of course be concerned that the bulk does not factorize in the spatial subregions. And in that case, you would want to apply, you would want to either do, apply, say this is some like introduce a cutoff, and then apply this in some approximate sense to that cutoff theory, or generalize this theorem itself to infinite von Neumann algebras, like we discussed has happened for Theorem 1. Like, Theorem 2 here has not yet been generalized to infinite von Neumann algebras like Theorem 1 has, but I say give it time because it took a few years for that theorem, and probably will take a few years for this one. But I think there should be no obstruction to this holding, even if you generalize, if you want to generalize it to infinite von Neumann algebras. Yeah, good question.
Sorry, Chris. So the generalization to infinite von Neumann algebras, would that be because of like QFT subtleties with defining factorization and this continuum limit, or would it be because of gauge constraints? What would be the?
You would want to consider both.
And you can fix both with these algebras?
Yes. The idea, like, so exactly. And so in the case of Theorem 1, both subtleties have been handled, and then the idea is that you would handle both of them also for this Theorem 2. I expect it to all go through morally exactly the same.
Cool, thanks.
So by product unitaries, I mean the following thing. So let's consider what I'm going to call a product unitary on little b. So I'll write it this way, U prod on little b. And I literally just mean some unitary operator that has a particular structure. That structure is that it factorizes across all, like this special tensor factorization we allowed for little b. So it would look like you act some arbitrary unitary on little b1, tensored with some possibly different, so maybe u prime, possibly different unitary on little b2, and so on, all the way to being tensored with some yet still different unitary on little bn. So you're on each of these factors in little b, you're acting some unitary that can be completely unrelated. They can be the identity if you want. But this is what I mean by a product unitary acting on little b. And likewise, I'll refer to product unitaries acting on little b bar, where I'm just, it's the natural generalization where you replace all the pieces of little b with the pieces of little b bar. And then a product unitary on both of them, on little b bar, would be you're just acting like some unitary on each of the different factors of both. Okay, so that's what I mean. This is a very specific sort of operator, and you can be like, why are we defining this here? The reason is that it just shows up in the theorem. It plays a privileged role. And I will try and motivate after stating the theorem why this sort of thing was inevitable, why it had to show up. It turns out it's important. And to jump ahead and spoil the reason, it's that this sort of operator doesn't change the entanglement structure among all the pieces. And so therefore it doesn't change the position of the entanglement wedge. And that's really important for getting something that's morally equivalent to the QES formula. Okay. So the statement, okay, so that was an aside when we're stating the theorem. And then now the theorem continues in this box. We'll say the following two statements are equivalent. Okay, so what do I want to do? I want to lift this up. And then here's, okay, so there's a statement 1 and a statement 2. Let me again write statement 2 first. Statement 2 is the statement, is the one that you're familiar with as kind of being the statement of the quantum extremal surface formula. So it's the statement that if you computed the entropy of capital B in the state you get by taking psi and mapping it to the boundary, by mapping it to the physical Hilbert space with V, that would equal, you know, again, the entropy of some bulk region, so here little b is playing the role of the entanglement wedge. So the entropy of little b in the state psi, plus this something like A, but now this A is gonna be allowed, this A is generalized from the definition in Theorem 1. It's a new A that reduces to the Theorem 1 definition whenever you add in the assumption of living in a fixed QES subspace. But more generally, it has a more general definition. And we're gonna take some time to unpack this because it's kind of cool. And then also this A is gonna have an extra argument. It's gonna be allowed to depend on capital B. That's fairly natural because you know, B appears on the left side, appears on the right side here. And then likewise, a similar statement holds for the complementary regions, like little b bar and capital B bar R. Okay, but statement 2 is actually going to be a little stronger than just that this formula holds. It turns out the right way to write a statement like this, that implies anything, is to ask this to hold not just for psi, but for all product unitaries on BB bar. Let me just call this U. So it holds for all states related to psi by acting a product unitary on them. So it's like if you look at psi and find its entanglement wedge, this is asking for the entanglement wedge of some other states to also be little b. What other states? Well, the ones that you can get by acting just a product unitary on the bulk. Now, this is kind of a new ingredient in the statement of the QES formula, right? We don't usually say that. Like Jeff never had to say this in his lecture when he talked about the QES formula. He never introduced product unitaries or said the QES formula demands that it holds for all product unitaries in addition to the state you're considering. That never came up. But it turns out that this is just true in gravity. We just always took it for granted, right? If you find the QES in gravity, you find some region, and then if you acted some product unitary, some operator that didn't change the entanglement structure, you wouldn't change the QES, its position at all. It turns out that's an important ingredient from the QI perspective that we just had sort of neglected, I claim, from the gravity perspective. So it's going to be there, and I'll further motivate why it shows up. But you have a question?
Yeah, and it's just more like a comment. Like, so it seems like there's you can get like many states out of these product unitaries, right?
That's right. Yeah. They
Like
all
I'm
have the
assuming
same.
these BNs are like many, right, in general, or
That's right. Yeah. So yeah, these could be like all the qubits in the bulk, and yeah, you could get many states by acting as product unitaries.
Okay.
But they all have the same entanglement structure.
okay,
Yeah.
okay.
Yeah.
So is it possible? Yeah. So can state connected by these product unitaries completely change the QS like in the black hole case from before?
Good.
Or-
So yeah, the point, and I'll argue this more carefully in a little bit. The point is that these will not ever change the QES.
Okay.
Yeah.
Good.
And they're exactly the operators that don't change the QES. That's why they show up.
So if I remember correctly, psi can be in the reference state, or the reference system?
Yeah, psi has support on little b bar, and the reference system.
So how would V map a state in the reference system?
Yeah, no, V is just acting on H code. It would just act on this part of psi. Right. So yeah, so it's going to map a state. So good. So psi. Right, so yeah, psi is a state on B bar, R. And V psi is a state on, I'll write it this way, is a state on H, capital B bar, R. The R part goes along for the ride.
As a follow-up to Gulow's question, and to get some intuition, what sort of operator would I have to act on this example where you have the black hole microstate and then thermal mixture of black hole microstates? Like, what operator takes me from one to the other?
Good. It's an operator that entangles the black hole with some reference system.
Okay.
Yeah, that's how you would, so you can create uncertainty by entangling it with some external system that then you would trace out when thinking about the bulk state.
And can I think about this effectively as a non-local bulk operator or something? And that's why it's changing the bulk entanglement structure?
Exactly, yeah. It's not what I would call, let's see.
Like, I'm trying to think about it without any reference. That's my, yeah.
Yeah, this question is a little subtle because, yeah, if you think of it as entangling it with some reference that you then forget about, it's not something that that process is not a process you would implement with a local unitary. But if you think of it as entangling it with a system that you then like keep holding on to, it is still something you can implement with product unitaries. But the fact that you're holding on to the R means that the black hole is not actually in a mixed state because you know what state it's in because you have its purification.
Can we do it without the R?
To do it without the R, it's more equivalent to like implementing this unitary transformation from a pure black hole to one that's entangled with R, and then throwing away the R. That throwing away is the non-unitary part of it.
So it's not even just that it's not a local unitary thing. It's just not a unitary.
That's
so
right.
It's okay.
Yeah, exactly. Because you're mapping from a pure to a mixed state,
Sure.
and so yeah.
Okay, thanks.
Okay, so this was condition 2, and then there's a condition 1. This is the one we're really interested in, right? Because the whole point of coming up with this theorem, more or less, was to say, we have the QES formula, we want to know exactly what it tells us about reconstruction. So is there some reconstruction statement that we can prove is equivalent? Here it is. The statement is that for all product unitaries on little b, there exists a unitary on capital B such that this guy reconstructs this guy, but in this in what I'll call a state-specific way. So the formula looks like before. Where if you took psi and then acted this product unitary on it, and then mapped it to the physical Hilbert space, you get a state that you could have equivalently gotten by taking psi, first mapping it to the physical Hilbert space, and then acting some operator on B. So the non-trivial statement is that this B exists that will get you to the same state. It wouldn't be true for, say, acting on B bar in general. Now, there's two reasons this is weaker than the condition 1 from theorem 1. Right? It looks kind of similar because it's still a statement about reconstruction. It takes a similar form. But also, I should say, a similar analogous thing has to hold for the complementary systems, like the barred systems. Okay, but I'm just not writing that. Okay. So one reason this is weaker than the statement of theorem 1 is that we're only promised here that we can reconstruct product unitaries. That's the first thing. The second thing is actually the more dramatic one. It's that this U is guaranteed to do this, to work this way, like, do the same thing that this guy did, but only when acting on psi. Okay. So for example, it's not guaranteed to work this way if the bulk state were something else. Right. It's only guaranteed to work this way acting on this state that we assumed, the state psi. So this is true, but not necessarily so this is the same exact statement, but phi is now a different state than psi, and it's not necessarily the case that this holds. So that holds, but this doesn't. In theorem 1, remember, it was state independent. It just said here it said for all psi this was true. Here that's not the case. And I'm emphasizing this because this is the biggest difference. And we'll see why it makes sense. But yeah, there's a question.
Is phi any other state?
Yeah, phi, let's just say phi not equal to psi.
Right. So is there what special assumption did psi have to all this state?
Yeah. So psi is the state that shows up in condition 2. So like assuming this for psi
Okay.
implies this, but doesn't imply it for phi.
Okay.
Like, you know, if you put phi here, that would imply this statement
Yeah.
for
Yeah.
phi.
Yeah. Okay.
There's a question up here.
Let's say psi is a black hole microstate, a single one. How many other microstates can I access using these U's?
Yeah, good. So that depends a little bit on how you factorize the bulk. So if you imagined that, so this is our boundary region B. It's this say larger than half region, and there's some black hole here. In the statement of the theorem, we were allowed to add this extra structure to little b if we wanted. So we could have treated, okay, you know, we could have, if we wanted, have treated the whole black hole as little b1. And then if this theorem held, like, so if this were true, it would have implied that we could get to any black hole microstate within this code subspace in this way. Like, so this U prod includes as part of it just like a general unitary acting on the black hole. Does that make sense? So, yeah.
So again, following up on Gulo's question, it looks in condition 2 like psi is special, but really the state that we're thinking about is like some equivalence class of U acting on psi.
That's right.
So the above formula will be valid for different phi as long as it's also related to psi via some
That's
local
right.
product. Okay.
So, sorry, let me say it this way. So if, let's say phi doesn't equal psi, but phi does equal some product unitary acting on psi, then you will be guaranteed that for some second product unitary acting on phi, you can find a reconstruction on capital B. So like if, let's assume phi equals U prod acting on psi. Then let's say U prod is not trivial. It's not just the identity or something. Then the first thing to say is that it's still not necessarily the case that this holds. Like, or by this I mean the same U that implemented, like, okay, so now, yeah, let me just write it down in a clearer way. So assume this top line, that phi is related to psi in this way. Now assume a second thing, that UB is designed such that U capital B on V acting on psi equals V U prod little b let's say it's a different uprod than this guy, or it could be the same, but let's just say he could be different, acting on psi. Okay, so we're assuming these two things. So there's some reconstruction of this uprod. Now let's act this same UB, but on phi. That's what you want. The question is, does this equal V U hat prod acting on phi? This is the question that you have. The answer is no. There will exist one, but it's not necessarily the same guy.
So yeah, I guess the U hat prod there, or like, if we just plug in psi is equal to U prod inverse on phi,
Yeah.
we're gonna get this thing. Is there gonna be like an obvious U big B on the left-hand side?
I think in general, no, because you'll have to reconstruct, reconstructing U hat times U inverse or something is not necessarily obviously related to reconstructing U hat.
Good, okay.
Yeah.
Thank you.
Yeah. Yes, Henry? All right, there's two questions. Okay.
Hi. Okay. Question about setup. You have big B and big B bar.
Yes.
Yeah, and then you have a disk. And suppose you have a black hole. Does disk is spatial slice go inside the interior of the black hole?
Yes, let's say it's like a nice slice.
Okay, so then if the small b1 and small b2, suppose those are interior.
Good.
Then those are different points on the slice in the interior.
Good.
So.
Yeah, good. So let's say we discretize, instead of calling the whole black hole B1, we introduce this extra structure that there's this spatial factorization inside. Call that little b1, little b2, etc. Totally fine.
Okay.
Good.
Okay. Yeah, just check it out.
Oh yeah, you
and
can
then, and then for now, the number of these dots inside the black hole is assumed to be smaller than A over 4, right?
For now, it's assumed to be smaller than A over 4. Okay. Exactly.
But so, going outside of the fixed QS subspace, you cannot reconstruct any operator anymore, but you can reconstruct only unitaries and just a small subset of those that you can write as a product of unitaries.
Good. I'm glad, because you're getting at the heart of what's really the difference here. Yeah, so the answer is that outside of this fixed QES subspace, we're no longer guaranteed that we can reconstruct every operator in a state-independent way. But what's actually true, so that's true. We're not guaranteed that we can reconstruct every operator in a state-independent way. But don't get the impression that this theorem is saying all you can reconstruct is product unitaries in the entanglement wedge. This is just saying that you're guaranteed at least this by this statement. And in general in ADS CFT, we actually usually have something stronger than this, stronger than just this. We might have that in this entire subspace, all of the entanglement wedges for all these different states, like psi, phi, et cetera, that are quite different, all overlap or something. That statement combined with this will imply that you can reconstruct operators that are much more general than just product unitaries. I'm going to show the precise version of that statement if I have time. But yeah, so I want to emphasize that because that's the right question. This is not saying that outside of fixed QES subspaces, all you can do is reconstruct product unitaries. It's just saying the precise thing that the QES formula tells you is this. But you can often do more than just reconstruct product unitaries in a state-specific way. You just have to use more information, like the QES formula applied to all these different states overlaps or something.
Maybe stupid question, but so for example, in the example that you gave before about the black hole that can have for different states, it can have different QS.
Yeah.
Why can't you, so in that case, there's only two QS. Why can't you divide the H black hole into a class of states that give you a gamma 1, a class of states that give you gamma 2, and then apply the first theorem.
And then apply the first theorem. Good, yeah. So you could
Except
say,
for maybe like states like the ones discussed before where you have some superposition or like.
good, yeah. So yeah, one thing you could do when talking about black holes is say, all right, if we took the whole black hole Hilbert space, like all of these different energy eigenstates, these black hole microstates, if we took them all at once, that's too big of a Hilbert space to do reconstruction. But maybe we just say, don't take the full thing. Take some fraction. Only consider that small subspace, and then just do this state-independent reconstruction in that small subspace. You can do that as far as it goes. That is a correct operation. I claim that's not allowing you to do as much as this will. Like this statement will include that possibility as something you can do. Like you can always consider a smaller Hilbert space, but sometimes you want to consider a larger one. Like you want to be able to like describe the experience of an observer who like maybe does the AMPS experiment, right? Like gathers all the radiation, which has many different states, and then like does some complicated unitary on like that general Hilbert space, and then falls into the black hole and measures something. If you wanted to describe that bulk process using the boundary, you would need a large Hilbert space to fit that whole process in, and so you need to talk about something like this, where like the code subspace is very big from the beginning to do that. Yeah. Good. Yeah.
So wait, just a clarification. So this applies for not all states psi, right? It doesn't apply for a generic state in H code tensor HR. It applies for a generic state in H code, and then there's a particular structure.
So yeah, there could be. I can interpret your question two different ways, I think. So one thing I can say is that the psi here was arbitrary. So this theorem will be true for any psi you pick. And this psi is like a completely arbitrary entangled state between H code and HR. Once you've picked that psi and up above, then the states that appear in conditions 1 and 2 are these two that are like, there's psi and then there's states related to it by product unitaries. But this theorem holds for general psi.
So it's, well, okay, yeah, so if you have a mixed state in H code, then you just have some purification of it, and that's...
Exactly, yeah. So we're not just assuming pure states in H code, it's even mixed states are allowed, we're just writing them in their purified form.
Yeah, thanks.
Yeah. Thanks for the questions. This was exactly the part I wanted to slow down and answer questions on, because it's the main result.
In that case, one more question.
Good.
Is it going to be like a minimal thing here, extremum?
Thank you for the segue. Okay, so
Okay, nice.
perfect. Yes, there is. So in theorem 1, it was a statement of equivalence between two things, and that was it. And then and that was it. And you could have asked, and indeed some people did ask when theorem 1 came out, where's the extremality? Like we say this is like the quantum extremal surface formula, but nowhere in this whole theorem did it say anything about S, like this being extremal over different choices of little b or something. And indeed in theorem 1, there was no such statement. It didn't, in some sense you didn't really need it because it was like in a context where all states had the same entanglement wedge. So the algorithm was simpler than find the minimal QES. It was like, pick this region, and then you can reconstruct that. But here, it's imperative that we find something like a minimality or an extremality condition, because we're allowing different states to have different entanglement wedges. So what is the entanglement wedge for psi, for example? Is that something we understand from this theorem? And indeed it is. the way it fits into the theorem is to say that there's a condition 3. And this condition 3 is actually not equivalent to conditions 1 and 2. It's weaker. So the statement, the theorem is that these two are equivalent, and moreover, both of those imply condition 3. And statement 3 is that this quantity here, so I'll write it this way, the area of this region little b plus the entropy of this region little b in the state psi, or, you know, in u psi for all u, but that this is less than or equal to the same quantity for a different region, any different region, b prime in the state psi. Sorry, this is supposed to be in the state psi. So what do I mean? What is b prime? So b prime. So this is a statement for all b prime, which are subsets of b bar. What I mean is sort of like this, where, you know, this region was little b, this region was little b bar, and then consider any other division of the bulk. Maybe this one given by this wiggly line we drew. So it's kind of like little b, but it excludes this guy and includes this guy. We can call all of those, we can call that b prime. So any b prime you could find would have greater generalized entropy than this. Okay, so it's minimal. Say again? Yes, anchored to the same, yeah, or homologous to the same boundary region, yeah. And I haven't talked about the homology constraint, but I will mention that once I describe to you what this A is. But it's the role of the subscript here. Okay, so one thing to note about this is that this is a statement of minimality, not extremality, right? So in real ADS CFT, we know if you have a boundary region B and you compute its von Neumann entropy, you want to use the quantum extremal surface formula. So you want to find a surface that's, and as Jeff mentioned, this is equivalent to the Maximin formula. He didn't really say much about it, but the idea is that when you find the extremal surface, it's a minimal surface in the space-like direction, more or less. Like, there's many space-like directions, but there is one, at least, in which it's minimal. But it's maximal in the time-like direction. So if you were to deform the surface in a time-like direction, the surface would have maximal generalized entropy under those deformations. This doesn't capture this sort of deformation in the time-like direction. And this is a very curious feature, right? So I'll try it in the last 5 minutes later on to tell you some very interesting future directions. One of them, the one that maybe I'm most concerned with, is continuing to understand this connection between, what the quantum extremal surface formula is telling us about bulk reconstruction. Because this is the state of the art, but it's really not about precisely the quantum extremal surface formula. It's about a special case that you might call the quantum minimal surface formula. And this quantum minimal surface formula shows up in ADS-CFT, but whenever you're at, say, like a moment of entry, like a two-sided black hole at t equals 0, some situation where you know that the procedure, like from symmetry, or perhaps that you know that the quantum extremal surface will definitely lie in some particular time slice. So all you have to do is find the minimal surface in that time slice. You don't have to worry about the time-like direction. But in general, you do have to worry about the time-like direction. We don't understand that from this code point of view. I would be really interested in figuring that out.
So do you think the reason why you got that result is because, like, is there more than just, so you picked a slice, so that is hinting to the fact that you're maybe working in a time symmetric situation or time independent situation, but is there, hitting in either in the theorem or some other computation, like some stronger like actual assumption of time symmetry or time independence?
Good, yeah. So, yeah, what is the assumption that we want to relax in order to get this more general prescription? Yeah, so I don't think at the level of this theorem it'll actually turn out to be a statement about time. Because we didn't actually say anything about Hamiltonians or time evolution, which makes this a curious problem. I think the assumption that's too strong is this one about the bulk. It's related to this bulk factorization. That if the bulk doesn't factor, what you need in gravity. Yeah, the extremality is related to the gauge constraints in gravity, and the fact that it's extremal under Wheeler-DeWitt evolution, which is like gauge evolution, and perhaps you want something like that in the code Hilbert space. Now you might say, okay, great, so we can just generalize this theorem to like the way Nico suggested earlier to algebras like gauge theories, and then maybe that will give us quantum extremality. Thought about it, it doesn't do it. You have to have something more complicated. So it's like, at least you probably want to relax this factorization assumption, but there's probably something more.
I guess like one crucial component must be the fact that you've assumed that, the B and B bar are just,
factorized.
Yes, but also that they're just like, you have this Riemannian slice. You told nothing about the space-time, right? So, nowhere, like this theorem knows nothing about the space-time in some sense.
That's true, but without having some Hamiltonian, and there's nothing about the time direction. Yeah. So that's true.
So somehow I guess you need to find a way of like defining B, like little b and little b bar in terms of some space-time homology region or something.
Yeah, that seems like a necessary ingredient, yeah.
So previously when we were doing it just for RT, was there some implicit way in which it was a minimal surface? Like by the definition of the area operator being what? Like here you have to, it implies this condition, but was this obvious before?
It wasn't obvious before, and in fact, it was not known before. Like that was one of the things that people said someone needed to figure out how to add that to Theorem 1 or something. And one of the contributions of proving this theorem was to do that, to show how the minimality arises. The reason why it didn't show up in Theorem 1, like Daniel who proved it didn't have it, was that to even write a statement like this, you need a definition of area that works for a general subregion. Where you pick a region like B prime, that's not the entanglement wedge, and you have some notion of area for it. And he didn't have that. He just had area defined for a single surface, the QES surface. Does that make sense? So he couldn't even write the minimality without. So once you take this definition of area and then apply it to his situation, you would get a minimality formula. So if he had come up with this definition, he would have been able to have this minimality as well. Yeah. But it wasn't crucial for him to find it, and he didn't. So he didn't, yeah.
Something that concerns me, like from the perspective of canonical quantum gravity here, is we seem to be fixing both a time slice, and so like some sort of extrinsic curvature, and the area simultaneously. Mm-hmm. Do you have a comment on that?
Yeah, so, I want to say, actually, I'm not really fixing a time slice, because I am and I'm not. So I'm actually just saying the bulk has some degrees of freedom, and we're just minimizing over those degrees of freedom. So, and I'm just saying, like in this picture I'm drawing, it's sort of an analogy. I'm saying you can think of it maybe as the degrees of freedom on some time slice, but really it's just like whatever the degrees of freedom of gravity are. Really, yeah. So,
I guess if we're talking about at least a boundary Hilbert space, and also a bulk one, but a boundary Hilbert space, it feels like a time slice on the boundary. But I guess that's not really a time slice in the bulk. So yeah, maybe it's just, yeah. Okay,
yeah.
Thanks.
So what I want to do, okay, if there's, feel free to ask more questions. What I want to do is really, I want to tell you what this area is, because it's important so you can fully understand the theorem. And then I would like to, in an ideal world, I would motivate why product unitaries made sense as a thing that showed up here. And then also, I would motivate how useful this formula is, because it seems kind of useless. And if you think about it, you're like, oh, I can only reconstruct product unitaries in a state-specific way. Actually, you can do much more if you use this cleverly. And then I would tell you future directions. Let me see what I can do of all this. So first, I'm just going to tell you what the area is. So, let me come back here. I'm going to erase this. What is this area? So as I said, this area, this function a of little b, is something that reduces to the definition from Theorem 1 that you saw when it should, but applies more generally as well. And it's kind of cool because it's like a way of defining area for a general V, or a general code. You might call V a code, like a quantum error correcting code. So it's like a way of getting geometry from entanglement. So to define it, the statement is the following. For any V, which maps some H code to some H physical, and I'm going to give the H code the following structure. So instead of writing little b's and little b bars, let me just use the same symbol for all of them. So I'm just going to say A1, tensor H, A2, and so on. Tensor H, A, N. So this is what I'm imagining if you just lumped all of the little pieces of the code subspace together, all those little factors. I'm just calling them all little a's. So V maps all of those to some H capital B tensor H capital B bar. Okay, so just assume you have some V that possibly, that admits this, and the Hilbert spaces admit this structure. And so perhaps in this language, B is some set of these little a's. Maybe it's like little a1, little a7, little a n minus 1, or something like that. Let me more generally say something like, I'll just keep that for now. Okay. Given this V, there's a special state, and we're going to need to talk about this. So it's called the Trojankowski state. It's a state on B bar, and then some extra reference systems, so I'm going to call little r1 all the way to little rn. So the little r's are like copies of little a's. And the state is given by, you take a bunch of maximally entangled states between all the little a's and their copies, like so little a1, little r1, little a2, little r2, and so on, all the way to little an, little rn. And then you act on all these maximally entangled states, this V. And so the V maps all the little a's to B and B bar. And so you get a state that's called the CJ state. Okay. And so the picture for this, which might help, is you're just, you have a bunch of, these are maximally entangled states, maybe like bell pairs. This is like A1, or I don't know. Yeah, let's call this A1, A2, etc. to AN. And then I guess R's go like this, R1, R2, all the way to Rn. And then you act V on all the A's, and you get out B and B bar. And then the R's just stick around. You're not doing anything to them. So then you have some state. So this circuit, which runs from bottom to top, gives you some state on these degrees of freedom. This is the pictorial way of writing this. Okay, so let's say in general that, so this was an example, little b. Let's say in general that little b is like a I1. So what is little b? I'm just going to specify some bulk region and call it little b. It doesn't have to be the entanglement wedge of anything. This is just like an arbitrary way of talking about some region that I'm then going to define its area for. So let's say it's little a, it's like a sub I sub 1, and then a sub I sub 2, and so on, all the way to a sub I sub m. Sorry for the 2 subscripts, but that's just a way to index it. So it's just some collection of these little a's. That's how I'm specifying my bulk subregion. And then I can call little r as the corresponding collection of little r. So it's little r sub I sub 1, little r sub I sub 2, etc. Okay. And then, now I can tell you what this area is. This a sub b of little b is defined as a von Neumann entropy in this Trojankowski state. So you take this state, we're computing a von Neumann entropy of what subregions? It's of capital B, little r. So when you chose capital B here, it goes there on the right-hand side. And when you're asking about a particular bulk subregion, that shows up because little r depends on it. So happy to talk more about this definition. But for now, I'll let it stand on its own and say it's really cool. We can talk more about it afterwards, of course. But let me ask you this question. Why this A? This is some very specific definition. Sure, Chris, it reduces to the 1 in Theorem 1 when it should. And sure, using it, you can prove this theorem that looks like a quantum extremal surface formula. But why, that's not a very unique reason. You know, how do I know that I couldn't come up with some other A that satisfied those same properties and was very different? Or maybe said differently, why should I think that when I apply this definition to ADS-CFT, it gives me like the area over 4G of the quantum extremal surface? And there is a reason. The reason, so I'm going to erase this. So why this A? The reason is that it's functionally unique. What I mean by functionally unique is that we can prove some theorems that say something very powerful, that let's say you did come up with some other definition of area that worked. You come up with some definition of area, maybe it's different from ours, you expect maybe it disagrees with ours in some important way, and just assume that your definition of area also satisfies a quantum minimal surface prescription. That's the only assumption that I want to make on your definition of area. If it doesn't, then I don't really care about it because we know the one in gravity does go into a quantum extremal surface formula. Just given the assumption that yours satisfies a quantum minimal surface formula, like ours, you can prove that yours has to agree with ours on all the important stuff. It has to agree on the positions of all entanglement wedges of all states, and it has to agree on the value of the quantum extremal surface area for all of these entanglement wedges. It'd be great to prove that to you. Don't have time, so I'll just say in this paper from last year in Appendix A, it's proven. Okay. So good. So this area is, I hope, nicely motivated. It's basically the functionally unique thing. And so we have this Theorem 2, which tells you, in general, what the quantum minimal surface formula tells you about bulk reconstruction. I'm not going to prove it to you. The proof is essentially the same as Theorem 1. Let me just say some reasons why it sort of had to turn out this way, where the reconstruction that you get had to be state-specific, so like the U's had to depend on psi rather than working on all psi, and why you can only reconstruct, you're only guaranteed to be able to reconstruct product unitaries. And, okay, so why state-specific? The basic reason is that whatever the quantum minimal surface formula implied, it had to be about one state. It couldn't have been a statement about many states, because the quantum minimal surface doesn't know about all states in the subspace that you chose. Like, if I just give you a state and ask what the quantum minimal surface is, I've just given you one state, and you found one quantum minimal surface. So whatever it's going to imply better be something unique to that state. So okay, it kind of makes sense that it turns out to be a state-specific thing in that regard. Theorem 1 got away with this much stronger thing, right? So you could just know that the quantum extremal surface formula held for one state and then implied reconstruction works for all states in your subspace, because you had this incredibly strong assumption that all quantum extremal surfaces were the same. So knowing it for one state told you it for all states, and then therefore it implied this reconstruction about all states. Okay. And then the reason why product unitaries show up is, again, because the quantum minimal surface can imply something only about reconstructing operators with respect to one particular state, morally in the entanglement wedge of that particular state. And operators other than product unitaries have the ability in general to change the position of the entanglement wedge. Product unitaries are specifically the operators that don't change the position of the entanglement wedge. I have a cool example where you might think, oh, wouldn't a general unitary acting on the entanglement wedge also not change the position of the QES? And in general, no. It has to. A unitary that doesn't respect this product structure, that maybe acts on all of the little b's, maybe entangles or disentangles them, can change the position of the QES. I'm not going to have time to write that example down if I want to tell you some other cool things. So now let me just say, as I've alluded to, this doesn't, okay, so you shouldn't take away from this that in these general situations, all you can do is reconstruct product unitaries in the entanglement wedge. No, the statement is that in the entanglement wedge, in this little b, the entanglement wedge of capital B for some state, you're guaranteed to be able to reconstruct product unitaries on little b. But maybe you can do more. It depends on other details. So the point is that you can, this has given you the exact information theoretic meaning of the quantum minimal surface formula. And so then you can use this equivalent statement, this QI statement of the quantum minimal surface formula, to prove other things you want, to prove anything you want. So, in practice, our best tool for learning about reconstruction is this quantum extremal surface formula. This tells you its QI meaning, so from that you derive all the other QI facts you might want, if indeed the QES formula implies them. Let me just say in words a theorem that's a good example of what I just said. So, you know, you might ask, how does this reduce to Theorem 1? Let's say we add in the assumption that all the entanglement wedges are the same. Like the QES doesn't change. So we pick some H code that maybe is sufficiently small that indeed all the QESs have the same position, even though we didn't necessarily assume it. They all do. Is there a way of using this statement to then imply that you can do this stronger sort of reconstruction that showed up in Theorem 1? And the answer is yes. There is a general theorem, and the upshot of it is this. Okay, the upshot of the theorem says the following. And this is important to know. So let's say we have some boundary region B, and we have some code subspace, some H code. So there's many different states in the bulk we're considering. Maybe in some there's black holes, and some there's not, or something. So maybe in one state, this is the QES of B, and a different state, this is the QES of B, and yet a third state, this is the QES of B. Okay, so let's say in our code subspace, there's many different QESs in different states, and then maybe there's these three. You can prove in many different ways, but there's a theorem that essentially says the following thing. It says that, okay, in this, if you just consider the portion of the bulk that is in all of the entanglement wedges, so the intersection over all entanglement wedges for all states in the code subspace. In this region, you can actually do this stronger sort of reconstruction that was guaranteed by Theorem 1. So in this region, which we'll call the RW, which is like the reconstructable wedge, it's possible, a stronger condition holds, provable from this and an additional lemma, that for any operator O little b in the reconstructable wedge of capital B, for any state, I'll say it this way, for all states in the code subspace, there is an operator on capital B. Sorry, I'm writing in a corner. I know that's annoying. There's an operator in, why did I write it this way? Operator on capital B that does the same job. So that reconstructs it for all states. Okay, so let me say again what we've done here. So the statement is that even in situations where there's different entanglement wedges in different states, one thing you can prove is that if there's a portion of the bulk that's in all of the entanglement wedges, then you can do this sort of reconstruction on that entanglement wedge, where you can find an operator that works in all states. Okay. So that's an important thing to keep in mind, and that's a theorem you can prove, say, from this equivalence.
Sorry, in this situation, H code is defined how? So how are you factorizing the bulk? You're taking the RW part and the rest?
Yeah, so let's say the bulk has this structure we've drawn here, where it factorizes into all these little BIs and B bar I's.
Oh, okay.
Yeah, just like the setup of Theorem 2, and then just like in Theorem 2, different states psi and phi can have different entanglement wedges. Mm-hmm. But if you consider all states like psi and phi, find their entanglement wedges, and then find their intersection,
and then
you can prove that this is possible in that intersection. even though outside of that intersection, you can't do this, but you of course can do this, you know, in particular states. But
Okay, so H code is just the Hilbert space of the intersection tensor, the part outside the intersection.
H code here, yeah. So H code, I don't want to change at all. It's always going to be the Hilbert space of all of these BIs, B bar I's, etc. And then
Okay, so but those BIs and B bar R's are for one particular state, right? Because there you're considering different states, right? And then considering the intersection of all the region inside the quantum extremal surfaces.
yeah. So the right. So the it's this spatial subregion that is the reconstructible wedge, and that's going to be in this language some union like B1, B7, B11, B13. Yeah.
Okay. Okay.
Okay. And good. So that's the power here. So let me just recap what we learned in this lecture series. So, so we reviewed stuff from a long time ago. So fundamentally in ADS-CFT, there you have the extrapolate dictionary. But a limitation there was it wasn't obvious how to write that, to use that to write bulk operators far from the boundary. But then about 8 years later, people came up with a way to use it, plus the bulk equations of motion to, in certain situations, do this HKLL style reconstruction, which was very explicit, but it didn't seem to work generally enough, for example, to reconstruct operators inside black holes. So then we fast forwarded again 8 years to talk about the more modern developments, which are that we've learned that possibly the best tool for learning about reconstruction is the quantum extremal surface formula. Then we saw how it's been used to learn about reconstruction. There was Theorem 1, which in these fixed QES special cases told us the meaning of the QES formula. But then we saw that we want to go beyond just fixed QES subspaces, and to do that, we needed this Theorem 2. This Theorem 2 then tells us the general meaning of the quantum minimal surface formula. So this is the general QI meaning of that, general reconstruction meaning. So this offers a way to derive whatever QI facts are implied by the quantum minimal surface formula. And that's what we saw. But that's not everything that we could want. There's a lot of interesting future work to be done. Let me quickly jot it down, because this is the sort of stuff that you youngins can probably figure out for us. So one is this. So we mentioned that for this state-independent style reconstruction that was promised to be possible in the fixed QES subspaces, right? So Theorem 1 said in fixed QES subspaces you can do this state-independent reconstruction. In that context, you can use things like the PETS map to explicitly reconstruct the operator. We had explicit reconstructions. Here, we have what we call state-specific reconstruction, where this guy is only guaranteed to work on psi. And it's such a new idea that we know very little about how this works. So we have no explicit way of doing it. This proof was non-constructive, and we don't have a construction that works in general. So especially for those of you who are more QI inclined, this I think is a very important thing, because a very important future direction. Is there an explicit state-specific reconstruction protocol that works, say, in general, something like PETS? This is like asking, is there a way of, in general, reconstructing operators inside black holes? Like, this is how high the stakes are. So that would be a very interesting future question. Another one is one that I mentioned earlier, which is the theorems we have are honestly about not the full QES formula, but about this special case called the quantum minimal surface formula. It's not obvious how to include time into this at all and get some statements about extremizing this quantity. So we just generally want to understand how dynamics work in these holographic codes. We're really bad at that. And I think a good first step is understanding how to get the extremality. And then lastly, in these theorems, we wrote down this V. It showed up for a good reason, because there is, in principle, this V that relates bulk states to boundary states. But at least in these explicit reconstruction schemes like PETs, it's very useful to know V explicitly. Right? So here V is used to say exactly what we mean by reconstruction, but to explicitly write down what the reconstruction is, generally that formula would have to use V. But we don't really know V in ADS-CFT. V is not something that we're handed. I think there should be some way to figure it out, maybe from the fundamental tools we have, like the extrapolate dictionary. But it's not obvious. And understanding this V better is a really important step into understanding how to reconstruct black holes, right? So, like if I have some black hole state, what is the V map explicitly? And maybe you can, maybe a good first step is to understand, for my JT inclined people in the audience, maybe a good first step is to start in maybe the simplest gravitational model, or the simplest model of ADS-CFT with JT gravity in the bulk. Maybe that will allow you to write down what V is. I think it's a very important direction. And with these future directions written down, and the QES partially explained and what it means for reconstruction, that concludes these lectures.
Thank you very much. Do we have more questions? Maybe one or so.
I'll ask one. Oh.
Yeah, no, go ahead.
Okay, so we said that we can construct product unitaries, or let's even say unitaries, in the entanglement wedge in general. We said that if we have some region that is within all possible QESs, then we can construct any operator. Is there any status as to the possibility of constructing non-unitaries in a region that is not in all the entanglement regions? Is there an exclusion statement, like that we can't do that?
That's a great question, and this connects to something that Gulu asked earlier. So yes, in general, if you have some region that's in, say, many entanglement wedges, but not all of them, there is a non-trivial statement you can say about what operators you can reconstruct there and like how generally they work. I don't have a good closed form way of telling you the answer. So like one way of summarizing some of the operators that can be reconstructed is that, connecting to what Gulu said, if you were to consider a subspace of your code subspace, if that subspace is small enough that this reconstructable wedge now includes that region, then you can say, okay, I can reconstruct an operator on B that works in that subspace of the code space. That's one statement you can make. So you're like artificially limiting the size. I think that it would be nice to, there's other things I think that you can reconstruct I'm not sure how to get that statement from this one, even though in principle, if it's derivable at all, it should be derivable from this, is that, say, computationally simple bulk operators are reconstructible, whereas computationally exponentially complicated ones, not necessarily.
Okay, so it means that if I want, for example, just a low energy operator, or an operator that changes the energy of some state by just a little, it should be more or less possible, or, well, actually I'm not sure if that's the
I think
correct way
that's
of thinking
basically
of
right,
it, so-
yeah, because as long as, yeah, your boundary region is sufficiently generic such that that doesn't really change like any of the entanglement wedges for any of the states, then you should be safe. So these low energy guys, probably generally safe and work very generally. Yeah. Yeah, good question.
There, hi. So since we have this map V, can't we just sandwich phi acting a little V or little b by V and V dagger? Like how does V phi V dagger differ from this capital O acting on capital B?
That's a good question. Yeah. Okay. Yes. Good. So, yeah. So the question is, all right. We talked about subregion reconstruction and like what you can and can't do with that. But what if I don't hamstring myself, don't limit myself? What if I just allow myself to use the entire boundary? If I consider any operator, even a black hole guy, say phi of x, then you might say, in general, I could just take this phi of x. If I have v, like I could just consider this operator, which maps them to the boundary. And maps them to the whole boundary, b and b bar. But okay, if I'm willing to use the whole boundary, maybe there's never an obstruction to reconstructing operators in the black hole. This is a great question. And in fact, you can prove that indeed, if V is an isometry, so if V, so yeah, the question was, what about OB just equaling this? And indeed, if V is an isometry, which means that V dagger V equals the identity, then of course, this equation is true because this equation does do the job. Because then consider any situation like this for any psi at all. So now put this guy here. This V dagger kills this V, and then this becomes, so this is like V phi, V dagger, V. This kills it, and so this left side is just V phi psi. So it looks like, okay, maybe if we just know V, we're done. We have, worked too hard to talk about subregion reconstruction. These questions we want to ask about reconstructing operators in black holes, they just reduce to using this operator. But in fact, this is important, and I'm glad you brought it up because I wanted to mention it. The trouble is that we don't think in gravity the map is always an isometry. It was an isometry in Theorem 1 by assumption. I didn't say that here for a good reason. Actually, it's not required here. It can just be any linear map. And we don't think that the map from the ADS Hilbert space to the CFD Hilbert space is an isometry. So it doesn't satisfy this. Why do I say that? The reason is the one that Jeff argued in his lectures. Let's say, for example, that we have an old black hole, and maybe we've been extracting the radiation and letting it go into some reservoir, or some R system. We have an old black hole, then in that situation, even though the CFT Hilbert space the state essentially has support on some subspace of dimension e to the a over 4g. In the bulk, we have semi-classical gravity, the sort of gravity that Hawking would have used, and it tells us there are more modes excited in the interior of the black hole than A over 4G, right? It tells us that the entropy of the modes inside the black hole is S, and S is much bigger than A over 4G. That's the definition of the page time. When the entropy of the interior radiation, or the exterior radiation, they're the same, becomes larger than A over 4G. So in that sense, for old black holes, there's more degrees of freedom in the bulk than in the boundary. So this V has to map a larger Hilbert space to a smaller one. You can't do that with a V that satisfies this equation. So this reconstruction won't, in general, do the job. And then it's important, it's essential that we take a step back, be more careful with our reconstruction schemes, and we're going to have to use these lessons. That's the reason. Thanks.
Great. I think we can, there were more questions, but I think we can continue over the coffee break.
Yes.
So thank you very much.
Thank you.